this first chapter is about introduction to engineering drawings. You're going to do a lot of drawings in this class, both by hand and in lab on the computer. So we're going to learn about why technical and engineering drawings are important, and then what the standards are for making those drawings. So where you put certain things, and the reason for standards, and we're going to talk a lot about standards this semester. And then the key points is that the drawings are used to communicate ideas, communicate the design. So someone else can either fabricate it or make it, right? Or at least review it and understand it and see if it's going to work for them. Okay. All right. So I'm going to go ahead and launch a poll. Okay, so what is design? All right, A, B, or C, or D, or none of the above. So it's a way to make something, making a part or a device look better, a strategic approach to problem solving, the work done by an engineer, or none of the above. So if you read the chapter, you'll know this, or did the ILM, you'll know this. But I just want you to start thinking about it and see where we're at. And give it a couple more seconds. All right. I think most of you, well, 75, only 75 of you voted. So if you're on your phone doing the lecture, the poll might be hiding somewhere. So you might have to like move things out of the way. Okay, gonna end the poll. So most of you picked C. Okay, which is a strategic approach to problem solving. Well, chances are that's probably the correct result. All right, so it's a way to approach a problem and solve it through drawings. Okay, so thanks for the hints on how to do it on a mobile device. So here's an example of a hammer that was designed to minimize transmitted vibration to the user. So the one on the left has like a rubber coating on the handle to reduce the vibration to the hand. You can imagine if you're using a hammer all day, that would be very important. Now for most of us, we use a hammer, you know, just to put one nail in the wall to hang a picture. It really doesn't matter, right? Some of us use the bottom of a bottle or a shoe or something like that to put the hammer or a nail in. Not the best tool for the job, but you know, if you're just doing it for one nail, it doesn't matter. But if you're a professional carpenter or something, you'd probably want something better to minimize that vibration. So this person had to design something, right, to solve the problem of transmitting so much vibration to the hand, because over time it can cause some problems, medical problems. All right, so we're going to do a little bit of a breakout. So we're going to do a 10-minute breakout. You're going to introduce yourselves again. So you're starting to learn everybody's names in the class. Some people might randomly appear that you've seen the last time, but try to get everybody's name, go around the breakout room, introduce each other, say a little bit about your background, try to be concise, and then while other people are introducing themselves, please write down their name and something about them. And then as a group, I want you to discuss for 3 to 4 minutes, how do you communicate a design? You know, so how would you communicate a design to someone? And then pick one person in the group or one person volunteer to write down what you guys come up with, and then you'll post it in the chat after the breakout session. Okay? So introduce yourselves and then discuss how you communicate a design, and somebody write it down and put it in the chat box when we're done. All right, let me get the polling going, or not the polling. Sorry, wrong button. Breakouts. All right, we're going to have about 4 people per room this time. So I'm going to open the rooms, and then you have to self-select. So you want to communicate your design, and most of you are saying through something like CAD and communicating through drawings and specifications and whatnot. Okay, so I'm not going to bother polling on this one, but you know, different ways of communicating could be a sketch, an engineering drawing, even an email if it's something more informal, and a napkin, right? There are people who draw on napkins when they have meetings in a bar and come up with ideas, and they actually use that as documentation for doing their design that way. Okay, a sketch is a really good way of starting the process. So you can see here, a person is trying to come up with a way of heating water or distilling water by using the energy they produce when they're exercising on their bike. Okay, so you have some sort of power generator, and you've seen people do that. There's some YouTube videos where someone made a blender that way, that kind of stuff, where they charge a battery using a bike, and then the batteries used to power other things. Okay, so a sketch is a good way for doing brainstorming, coming up with some initial designs. And that's one of the reasons that we're teaching you how to do engineering drawings by hand as well as on the computer. If you can sit down and sketch out an idea on the board or on your notebook when you're meeting with potential customers and you're kind of hashing out some kind of idea, it's good to be able to do it by hand. Okay, quick and dirty. So it's a good start. So how do you communicate that? You can do an email with specifications. You can do Snapchat. You can do a sketch of the concept. You can do a drawing, or you can do a technical and engineering drawing. So which one of these do you think is the best way to do it? Let me go ahead and start a poll real quick. Yeah, I think you guys have got this one. So it's a technical drawing, right? You know, go ahead and end the poll. So here are some examples of technical drawings. So the one on the right is an older one from probably 150 years ago, probably 100 years ago. I think there's some electric motors and stuff in here, thermostats. So anywhere from 70 to 80 years ago would be my guess. And they used to do all the sketches by hand, right? And I like that drawing on the right side. It explains things really well. The numbers are item numbers, which are explained in another page of the documentation. You've got some cross-sectional views with these hash lines here. In fact, the type of hash marks they put here indicates what kind of material it is. So there's specifications for that as well. You'll learn a little bit about that later. So this is a cross-sectional view, so you can see the inside of it. If you just drew it from the outside view, you wouldn't know what was going on inside of it. Okay, and the one on the left is something you're more familiar with AutoCAD. It can produce those kind of sketches for you, engineering drawings and technical drawings, okay? So if you can, in the chat box, who do you think drew this? right, everybody's saying Da Vinci. Oh, someone said I did it. No, I'm not that good. I wish I was that good. Yeah, so Leonardo da Vinci was quite the engineer as well as artist. So he would make a lot of mechanical drawings. He made a lot of money, or at least he survived during the Renaissance by drawing out public works type projects and conceiving public work things. So yeah, Leonardo da Vinci, I mean, if you just Google him, you'll see all kinds of the cool sketches he did. And it's not just the artistic side and the anatomy, but also he was drawing mechanical things and even military war machines. So he did the first drawing of a tank and all sorts of things like that. So there's a lot of cool stuff he did back in the day. And that's around the 1500s, I believe. This is when he was alive. So it's quite remarkable, you know, that he was that advanced at that time. So technical drawing can be used as a noun or a verb, right? I'm drawing something. I'm doing a technical drawing, or it could also be the actual product, which is a drawing. So it's a noun. It's a process of creating an engineering drawing, right? Or it is a set of drawings that communicate the idea, a schematic, a model, that sort of thing. Okay. So a type of technical drawing used to fully and clearly define requirements for an engineered part or system. That's an engineering drawing. So it's a specific type of drawing. So this is telling you what kind of materials to use, typically, specifically where the holes are drawn or made, how thick things are, the placement of any kind of key features. Okay, here it's telling you it's steel, it's 1020 steel. The tolerances, which you'll learn more about later in the semester. Okay, what it's called, what the company name is, and then who drafted it, who checked it, and who signed off on it, the engineer who signed off on it. So a lot of drawings have to be signed off by a professional engineer, a PE, that has taken the PE exam. So they know what the laws are around signing off on engineering stuff. But the actual drafter could be a technician that knows how to draw up things, right? But the engineer needs to sign off on it. Okay. So there's a close-up of it. So there's a lot of information in this drawing. Okay. We'll do another poll. I like polls. Okay, so what does CAD stand for? A man that behaves dishonorably, a coronary artery disease, Canadian Association for the Deaf, computer-assisted diagnosis, or computer-aided design. So think about as far as a mechanical engineer is concerned. Give it a couple more seconds. All right. So yeah, it's considered to be computer-aided design as far as this class is concerned. So if you have a quiz or an exam question that asks what CAD stands for, it's computer-aided design. Okay, we always think about AutoCAD, right? Because they were the first real popular ones, and now we've got SolidWorks and PTC Creo and that sort of thing. So AutoCAD is now called Autodesk, I believe. All right. So computer-aided drawings or computer-aided designs. The computer-aided drawing refers to software that allows you to create drawings. So what's nice about SolidWorks is you start with like a 3D depiction of your widget, and then you can create the orthographic projections from that. And what you're going to learn in the hand drawing part is you're going to start with the orthographic projections and then work backwards and do the pictorials from that. So your brain will learn to go both ways. How are we doing on time? Oh, 10 more minutes. All right, standards is a big deal in engineering. Everything's got standards. So standards. So I'll give you about 30 seconds to a minute. Try to think of why we would even need standards. You can come up with an example why you would use a standard, or why you even care that we have standards. You know, why do we need them in engineering? Anybody think of anything? Oh, make drawings universally understandable. That's good. A common understanding, clear communication and accuracy, to make the sharing of ideas easier. Sure, all good. These are all very good answers. So you guys can look through the chat box and get an idea what other people put. Minimize drawing, reading, manufacturing, and inspection mistakes. That's a good answer. And when you write answers, you know, try to do more than, oh, my phone is yelling at me. Pardon me. Yeah, so the standards are real important to keep the miscommunicating down and that sort of thing. So why do we need standards? To minimize drawing, reading, manufacturing, and inspection mistakes. And international communication is key, right? If everybody does it the same way, then someone might be manufacturing what you designed in, say, India, right? They have lots of machine shops there, and they're really good at mass producing metal components and machine components. And it's a little less expensive, labor's less expensive there and whatnot. So your company might design something here, you know, make a few parts, make sure the design is correct and it's going to work. And then you've got to communicate it to someone in India that'll make 10,000 of these parts, right? So if you don't follow standards, and all of a sudden they're going to assume something in your drawing or your design and make 10,000 parts that aren't quite right. Okay, so keeping miscommunication low is great. Anybody know what ASME stands for? Go ahead and put it in the chat box. Let's see who can do it first. ASME. Everybody's Googling on their phones. No one's put anything. Oh, there it goes. Yeah, American Society of Mechanical Engineers. Very good. So I would advise you to go look these guys up and try to join as a student. It's cheap for a student. I can't remember what they charge now for students, but it might be 10 or 50 bucks a year. You get access to a lot of cool information. Oh, just join, 25 bucks plus tax. Well, thank you for that information. So that's not a terrible investment. Once you become, you know, professional, you're going to be charged like 150 bucks a year, 200 bucks a year, depending what bells and whistles you go for. But as a student, it's a really good deal. They do have things for students. They post internships there. They have webinars on how to write a resume, an engineering resume, and those kind of things. Okay, so we do have a student chapter of the ASME you can join. I'll probably be getting some information from that group, and they may do a virtual presentation to you all during class time. So we'll probably see that happening in the next few weeks. And it would be really good for you to join the group. One, you get to know the upperclassmen. They're usually the officers, the president and vice president, treasurer, and all them. But they can give you advice on what classes to take, where to go find internships. They also have professionals come in and talk to their group. So you might get to meet some professional engineers in aerospace at Sandia and that kind of thing. So I would go ahead. I would go ahead and consider joining ASME. You can go to their website and see what kind of things they have. It's nice to put on your resume, that you're a member of ASME and IEEE and whatever other things you want to join, as long as you get something out of it. Someone's put some more stuff in the chat box about an app called Researcher. You get free access to hundreds of research papers. Very cool. You can also look up research papers through the UNM library, and it's free to you as well. Okay, so a lot of the journals that you would normally pay for if you were to subscribe to them are free from the university. So as long as you're a student, you have access to that as well. So this is all good information for you guys. Okay, the last bit of this lecture is a history of drawings. So, blueprints is what we've been doing for decades. We still use them in construction oftentimes because they can roll it out on a big piece of plywood or a table at the job site and look at the specifications for the house or building or whatever. They used to be used a lot in aerospace. Now everything's on the computer. Okay. So engineering drawings also provide you with tolerancing. And we're going to have a chapter on that. They provide annotations, so special notes regarding how to what's important about the manufacturing of this part. Parts lists can be included in engineering drawings, so it's a set of drawings, right? And any other information that's important. So whatever is needed for manufacturing and quality control goes into the engineering drawings. So the tolerancing is, it's got to be 1 inch plus or minus 1/10 of an inch, or 100th of an inch, or 1,000th of an inch, So it gives you an idea of how much slop you have. And of course, the tighter the tolerance, the more expensive it gets. Engineering DWG format and content. So that's a drawing. These are different sheet sizes. You can read about this in the book. Okay, here's an example of a drawing. So you've got 2 orthographic projections. So you got a front view and a top view. That's all you need for this to fully represent it. You don't need a right side view. And this is called a pictorial. It kind of looks like a 3D version of your orthographic projections. So these are the 2D layouts. Okay, you have zones. This is usually used for complex design. So when you're talking about it to a customer or to a fellow engineer, you can tell them what zones you're talking about. So F6, look at F6. That gives you the detail of this part. So for very complex drawings, you might need to use zones to hone in on certain areas. You can add notes to it. There's title blocks, right? Tolerance and projection blocks and that sort of thing. Okay, the drawing scale expresses the ratio of the object size as drawn to its actual physical size. Okay. You have drawing notes in there, so you can put things like a particular requirement or information necessary to manufacture it properly. So an example of a note would be all rounds and fillets are 1, 2, unless otherwise specified. So that means you want a certain radius on all the edges, right? So sharp edges, most of the time we don't like because they're sharp and they get hung up on things or they can injure folks. Title blocks give you a lot of information about the part. Okay, revision, size, scale. You'll have a homework assignment on that. So you'll have to, like match up the different parts of the title block. So that'll make more sense when you do the homework. I'm not sure if Raul's requiring title blocks. So, but for your final project, it will look like this on every page. You'll have a title block, revision history, all of that. And then you'll have your drawing area for each part of your design, your team design. So try to learn all this stuff because you're going to need it for the final project. You have tolerancing and projection blocks. So projection tells you if you're first angle, third angle, and that kind of thing. We'll get more detail on that in the next chapter. Okay. So that's it for today. So let me unshare.